webinar. I'm Shraddha and I'm your host for today. Today's topic is on impact of wear on quality and output. We have two speakers on the panel today, Raghavendra Jairam and Dr. Prakash Hadimani. First, Raghavendra, who has over 20 years of experience and handles sales for Middle East and Turkey. Earlier, he was heading technical services at Steer. He will give you an introduction about STEER and our program. Thereafter, Dr. Prakash Hadimani will cover the technical aspects of today's topic. Let me give you a brief about Dr. Prakash. Dr. Prakash has completed his master's in polymer science and technology and has a PhD in polymer blend. He heads the application department center at STEER headquarters at Bangalore. We also have an Q&A sessions. You will find a Q&A tab at the bottom of your screens. Please drop in and ask your questions about today's topic. Dr. Prakash will answer them at the end of today's webinar. Please also participate in the polling questions at every break. We will have 3 such questions and we will really appreciate if you can respond to each one of them. Without further ado, let's go now to Raghavendra to commence today's webinar. Over to you, Raghavendra.
Thank you, Shraddha, for the brief introduction. I welcome all the participants for today's webinar. Today's webinar is on impact of wear on quality and output. So before we start with the session, I would like you to introduce to our company Steer Engineering Private Limited, which is located in Bangalore in India. Steer makes advanced material platform technology that effectively transforms and functionalizes materials in the field of plastics, pharmaceuticals, food, pharma, and biorefining. Steer has a global presence with 4 global offices worldwide, one in India, China, Japan, and USA. We have 4 application development centers, and the application development center in India is the Global Application Development Center, and we have 2 manufacturing units in India, which is in the southern part of India. We have 10 satellite offices, and we are an organization with 500 plus employees, and we have 100 plus patents applied for. We are proud to say we have sold more than 950 extruders till now to different parts of this globe, and we have more than 1 million elements sold till today. We have supplied to more than 50 countries till now, and we have sold about 8,000 plus EPZ parts to TSCs worldwide. As we have 2 manufacturing facilities, one in Coimbatore and one in Bangalore. Coimbatore, we have a foundry for tool steel, barrel, elements, and gearboxes. And in the Bangalore facility, we make elements, barrels, shafts, and extruder. We have our own proprietary metallurgy for making elements, barrel, and shafts for EPZs. And also we make components like gearbox, feeders, vacuum stuffers, and panels. Steer makes extruders with 3 different platforms. We call the series as Omega series, Mega series, and the Alpha series for different applications. And we make processors for pharma and food. We also do plant engineering for plastic, pharma, and food intermediates. Steer is the only machinery company which makes from tool steel to machineries. We serve to various industries with our latest technologies like polymer, biomaterials, powder coat, construction, pharmaceutical, and food. For polymer, we give end-to-end solutions for engineering plastics, PP compounding, color master batches, filler master batches, and recycling polymers. And for the biomaterials, we give equipments for PBAT, TPS, and filler applications, PBAT, natural fiber and powder applications, PBAT with lignin, PLA, starch and fillers, PLA, PBAT blends, and starch. For the powder coat, we make our equipments for posing polyester and epoxy with color pigments. And for the construction, the long glass fiber reinforced PVCs and HDPE for structural, for borewell and non-pressurized pipe applications in construction division. And for the pharma, we make hot melt extruders and then single step granulation and drying sizing equipments. And in the food, we supply our equipments for cereals and snacks industries, animal feed and pet feed industries, and meat analogs. In the EPZ business, as a snapshot, we wish to say we have about 20% market share for the replacement EPZ parts for extruders globally. Till now, we have sold more than 6,000 plus EPZ parts worldwide, and we have sold to more than 50 countries. Our annual capacity for making EPZ parts is about 72,000 elements and 2,400 barrels and 1,200 numbers of shafts. This is not all. We are increasing our capacities as we are capturing more and more market share. And we have a wide range of MOCs with options for wear resistant series, corrosion resistant series, powder metallurgy for soft coat, crest welded and surface coated. And as a proprietary MOC acryloy grades, we can supply in WR5, WR6, WR7, WR10, CR5, CR6, and CR15 grades. Our supply of EPZ parts are for different diameters of extruders, starting from a range of 10 mm to 300 mm in diameter. These are the snapshots of our application centers that we have worldwide. One is in India, one is in China, one is in Japan, and other in the USA. So for all these application development centers, India is the main global head center where we conduct more and more trials. Our success rate is also very high. We have converted more trials into orders. Coming to the platforms of the extruders that we make with the D by DO different ratios, we have Alpha series with the DO by DI of 1.49. We have Mega series with the DO by DI of 1.55 and Omega series with a DO by DI of 1.71. So as you can see from the slide, in the Omega series, we have a better channel depth, free volume, and with the Alpha, we have a very good shear rate. And again, in the Omega, we have a feed capacity, which is more than Alpha and Mega being the bit range. So these three different platforms are suggested to our customer based on different applications. So for very high shear materials, we suggest Alpha, and for torque limited and shear requirement, we suggest Mega series. And for the materials with low bulk density, low SMB, and low shear, we always suggest Omega series. Before we go into the actual webinar of impact of wear on quality and output, that which Mr. Dr. Prakash is going to take today. So we learn about, as we know, wear is an inevitable, it's going to be there always. But when we measure the wear and when we study the wear pattern and replace the elements and liners at regular interval, so we can avoid many side effects of that. So that we are going to learn today from this session. And I'm happy to hand over this session to Dr. Prakash now to take this forward. Over to you, Dr. Prakash.
Thank you so much for the introduction, Raghavendra. The extruder process, Joe, the impact of wear on quality and output. This is very important when in the twin screw extruder, the EPZ section, what we call it is, it's heart of the extruder. If the heart of the extruder, you need to know the what is happening inside the extruder. And day-to-day activities like every month, you need to understand the behavior of each element is in terms of what you can is a wear out, like how much it's a wear out and what is the quality of the final your product. Because you are looking for a mechanical property, like for example, like 25 to 30 megapascal, whether all the quality requirement parameter after 1 month, it is maintaining or not. And also the throughput, what you initially decided, 200 kg per hour for that particular product, whether are you achieving the throughput or not. And also inspection of EPZ section means every quarterly or 3 months in a once, so that you need to understand the pulse of the extruder. Like when you go to doctor will check and tell you what are the diseases, like that. Today's session, we are going to discuss, there are 3 case studies. First, we are discussing on the introduction of wear pattern, how it happens, and also each zone, how zone wise, okay, the segmented zone wise, what is going to happen, each function of the zones, and also it's followed by the case studies. First case studies is impact of wear on the quality, and we have selected, there are 4 applications. One is PP, tall 40% weight percent, and also second one we have selected LADP blue monopigments 40 weight percent, and the third one LADP blue 25%, and the combination another 40% calcium carbonate, and the lastly LADP carbon black with a 50%. And these 4 case studies we are going to discuss, and using these applications, and we understand the wear pattern in the twin screw extruder, how the behavior of the elements, screw elements. These case studies, then lastly, again the same one, we repeated the case studies on impact of wear on the throughput also. First, we decided on the quality. Second slide, we are discussing on the output behavior. And also ROI, we need to discuss. Extruder processing zone is the heart of the twin screw co-rotating extruder. It helps to achieve desired performance of the product and the quality. And if you talk about the EPZ, intake, melting, atmospheric venting, mixing, and vacuum is all, and finally it's a metering section. It's all as a different role. Okay, that's why we call it as a twin screw extruder, as a cocktail extruder. Because each zone give you the required function, and this study utilizing of these automotive applications and also color master band. The polymer, when you take any polymer pellets, okay, initially it becomes too hard. We need to soften the polymer. How you soften the polymer? There are 2 ways soften the polymer. One, you apply the external heat in the barrel so that the polymer gets heated up and start softening. And the second one, you're applying the shear through screws. When the shear increases to achieve a required level of melting, mixing in the short time. Because if you talk about the melting happens in the short time, like 2 seconds, 3 seconds, we are talking about. To form a viscous material, this we observe the massive transfer of mechanical energy through achieving this particular melt. And during that time, there are a lot of flex, mechanical flex on the screw and screw to barrel, and we call it as a wear and tear happens in the EPZ section. And there are some materials we add the polymer like a polycarbonate, nylon 6, and some fillers like glass fiber and boron, tal, calcite, silica. These are some abrasive materials enter into the twin screw extruder. It causes abrasive and corrosion. During the wear in the compounding, due to the wear happens when the polymer enter into the twin screw extruder, there are 2 body, like contact between the screw to barrel and also the action of the material in the screw barrel. These 2 phenomena takes place to cause a wear. And again, if you calculate the fast wear, medium, slow wear rate, the fast, medium wear, it all depends on the material. If you talk about material, what material we use, what filler you are going to use, And also, when you increase the screw speed, decrease the screw speed, and also it leads to the quality of the product. Now, we are going to discuss on each zone the behavior in the twin screw extruder. If you talk about the first zone, is what we call it is an intake zone. This helps you the hard material enter into the intake zone. It just moved to the next level. During that time, what phenomena happens? The feeding of like a crystalline polymer, amorphous polymer, such as a polyamide and polycarbonate, because polyamide is a crystalline polymer and polycarbonate again is amorphous. Both are hard material, and some of the recycled material polymer also. Once it enter into the twin screw extruder, the contact between screw to screw and the barrel, there is a, we call it as a abrasive wear due to the contact between the screw and the barrel, because we need to melt the polymer. And the feeding abrasive fillers such as titanium dioxide, calcium carbonate, and this will be the to improve the dispersion, because the screw to screw and the barrel clearance, and also to get the improvement dispersion causes abrasion and of the surface due to the particle flow, because the particle has to flow into the these two sections, the screw and to the barrel. That particular gap, your the material has to move. What are the effects? Due to the wear and tear in the first intake zone, what is the effect we are going to observe? In the twin screw, the loss of feeding capacity and also the intake capacity drops down drastically. For example, initially, if you are calculated 100 kg per hour, maybe there is a 10% reduction after 3 months. This is the effect of wear, and also started hopper flooding, and the material starts stagnating there. It doesn't move to the next level. Now, second section, we are talking about the melting and the compression zone. This is the melting and the compression. Melting is here and the compression. Once the polymer move to the next level, it starts softening this particular area, because the compression, we call it as, it compresses the material slowly, and through kneading section between the screw to the barrel, the melting takes place. The compression kneading elements experience high level of mechanical flexing, because between the screw and the barrel, due to that, the rubbing against the barrel surface causing abrasive wear and also adhesive wear. Because each particle and also polymer experience enormous pressure and stress concentration on the polymer. Okay, and this is because of the barrel and the screw, the wear and tear is placed. And the flow of abrasive particles which the melt during the melting and mixing causes high level of abrasion wear, because the particles movement causes abrasive wear. And the presence of moisture leads to the corrosive wear, because the hygroscopic material like nylon 6, these are the hygroscopic material, lead to corrosive wear. What is the effect during the first section? If you are talking about this melting section, loss of melting capability and capacity, and with significant impact on the compounding process, like your dispersion comes down drastically when you are adding particles with the polymers, and dispersion reduces and quality reduces. This is the effect at where happens during the melting zone. And the second addition of after melting the polymer, if you add the filler particles from the side feeder, again, this called as a mixing and melting. The same effect happens in this particular zone. This is the feeding abrasive fillers from the side feeder, reduces the screw and barrel contact while the wear occurs due to the presence of abrasive materials. And also again, the effect of wear. What is the effect? Loss of dispersion and also loss of mechanical property, decrease in the mechanical property, and also back venting happens because the wearing takes place when during that back venting of the filler and block the complete area and reduces the throughput drastically. A next section is important section is we call it as a vacuum zone. Vacuum zone, the flexing of screw during the, because if you hold the material in the metering section, this is what we call it as a vacuum zone. If you fold the material, the more back pressure in this particular metering zone, it starts flexing your screws, and also wear and tear happens in this particular zone because of the back pressure. Because material stay for a longer period of time, the wear and tear happens high. And the flexing of screw in the metering zone leads to the abrasive wear in the end zone of the extruder and corrosive wear due to the presence of unmolten materials and also monomers. Unreacted monomers stay for a longer period of time. Moisture and other volatiles organic compound, if you stay in this particular section, there should be a corrosive wear. What are the effects? Porosity, voids appears in the final compound, and also your vent completely blocked, because if the screw conveying screws, this particular wear and tear happen, this zone is the movement of the flow, the forward moving stops directly and it blocks the vent in particular vacuum zone. The vacuum level drops due to the inadequate sealing efficiency, and also the pumping action reduces in the metering section because this area, its pumping action drops drastically because of the wearing.
Thank you, Dr. Prakash. Here is our first poll question. Please select your answers from the list of options displayed on your screen. You have 30 seconds to select it. Considering our expertise in metallurgy, do you like us to contact you for offering best MOC for elements and liners for your application? Yes, no, or not sure? All right, 3, 2, and 1. Let's see the results. 70% says yes, 10% say no, and 20% not sure. Also, if you have any questions on the ongoing webinar, please drop into the Q&A tab at the bottom of your screens and kindly ask your questions. All right, let's go back to Dr. Prakash to continue with the webinar.
Thank you. Okay, now after the wear pattern happens, now we are going to discuss on the case studies on some of the applications, what's the impact of wear on quality. First slide, we are talking on the quality. The later stage, we are discussing on the output. We have selected the first applications, PP talc, 48%, on doing the split feed method. Here, we fed the polymer from here, polypropylene, and the melting takes place during this section, and split the talc from here, and there are two side feeder we have used fed from here and here, and you use 40% talc. First, the first kneading section, we are talking about the compression kneading section, we subjected to wear. We did the OD reduction of the screw. For both the screw, we have initially started with a no OD reduction and took the trials, collected the sample. And second line, 0.6 millimeter means 0.3 per side of the screws, and in the first kneading section. And the second section, third needing section, no OD reduction. It keeps the same constantly. And second line, third one, 1 millimeter OD reduction, 0.5 per side. Second and third, no change, no OD reduction, 1.5 millimeter here, 0.75 per side. Second and third section, needing section, no OD reduction. 1.5 millimeter and both the side you say 0.75 per side, and second section and third section again 1 millimeter OD reduction means 0.5 per side. Both the side you said 1 millimeter. Similarly in the third needing section. And the sixth one, 2 millimeter, 1 millimeter per side in the first needing, second needing 1.5 millimeter, and the third needing 1.5. We went up to 2.5 and 3 millimeter respectively for all the zones. Like a second zone is 2 and 2 millimeter, and the third 3 millimeter, okay, 1.5 millimeter per side, and 2.5 millimeter and 2.5 millimeter second and the third needing section. We have selected the barrel configuration, intake for feeding the polymer, melting, and the talc fed from both the side feeder 25 and 15% from the second side feeder. Without OD reduction, the PP talc pellets 40% if you see the glossy and the pellets and disperse completely, and we got the required quality. But in the right hand side, this slide talk about after OD reduction and the dispersion quality reduces and the quality of the product reduces. And also there is no much shining on the product, and dispersion, the homogeneity is not there. We see still rough surface on the pellets. The first one is tensile strength. Without OD reduction, 24.25 megapascal. And if you come to the, sorry. If we talk about first needing section, 1.5 millimeter per side 0.75. If we are at 23.96 megapascal. The acceptable what we decided, if you go up to the first needing section 2 millimeter, 1 millimeter per side, it is acceptable what we decided, but it is depends on the industry standard. This can be maybe your benchmark maybe stops even at 23.96. Okay, then you have to again rework and do the like a measurement for your elements. Every frequently you have to measure your elements. And in the second and third needing section 1.5 millimeter, and finally the first needing section 2.5 millimeter means almost 1.25 per side. Second and third needing section is almost 2 millimeter. This shows after this section wear and tear is high and your quality tensile strength drastically reduces. That shows the increase in the wear pattern, reduce in the tensile strength. In the automotive industry, flexural model is very important. The stiffness is very important. Without OD reduction, we are at the megapascal 5365 on the flexural modulus. And in the first needing section, and come to up to here, the first needing section 1.5 millimeter and 2 and second 3 needing section 1 millimeter is acceptable. So that we are getting a flexural modulus 3422 MPa. But in the after that, suddenly there is a drop in the flexural modulus. The first needing section 2 millimeter, we say 1 millimeter per side, and second and third is 1.75 per side. And this wear pattern is very high, so that your flexural modulus reduces, so that you can then start thinking the measurement of the elements, whether which section you need to replace, which one is give you the better mechanical property. Similarly, the impact strength also, without OD reduction, we are getting at 6 kilojoules per meter square. And in the last section, if you see that the first kneading section, the red section you're talking about, it's almost reduced in the mechanical property of the impact strength. The first kneading section, 2.5 millimeter, if you say 1.25 per side, and the second and third section, 2 millimeter, and it is almost ending stage, so that you need to replace your elements and check the measurement of the kneading section. And we are coming to discuss on the second application, LLDP color master batch. Okay, this is monopigment. Here, its a vital role is the dispersion. Is very, very, very important rather than the throughput. Here also, we follow the same pattern, right? One kneading section and second and third kneading. But in this case, all the material pre-mixed and fed from the intake section along the way and understand the dispersion quality. And here also 0.6 millimeter, 0.3 per side, and second and third section, no OD reduction. Followed by similarly 1 millimeter and 1.5 millimeter. In this case, 0.75 per side, but in the second section and third section, 1 millimeter, 1 millimeter. And the last one, 3 millimeter, 1.55 per side in the first kneading section, and in the here 2.5 millimeter in the second and the third section, also 2.5 millimeter. Here we have selected 3 applications. One is LLDP blue pigments, 40%, LLDP 25% blue pigment, and the combination of calcium carbonate is 30%, and the LLDP also carbon black with a 50% loading. When you check the dispersion quality, the initially without OD reduction, we are getting 1.9 bar per gram. First kneading section and the first kneading section where you have 0.6 and 1 millimeter means 0.5 per millimeter. We are almost at the benchmark, 3 millimeter, 3 bar per gram. What we are talking about, the dispersion level. After the first kneading and second kneading and third kneading, it is increasing the FPV value, means the dispersion quality poorer and poorer. This is not acceptable. So that you need to measure your screw design elements. This is a combination. If you see the LLDP, blue and calcium carbonate pellets, the left-hand side, it's so shiny and without OD reduction. The right-hand side is with the OD reduction. There is no jetness in the pellets. It looks rough on the surface of the pellets, and also the dispersion, the poor dispersion quality. In the case of the combination, again, the calcium carbonate and the blue, here, because 25% only the blue pigment, so that the dispersion is easier compared to the 40% monopigments, other pigment. This is the combination. Now, up to the first kneading and the second kneading section and the third kneading. The first kneading, what you are talking about, 1.5 millimeter, 0.75 per side, and 2 and the third kneading block 1 millimeter, if you say 3.08 bar per gram, it is acceptable. So that after this, then where you have for this combination, your screw elements wear out has to be measured. So that 4.2 is going because the wear rate increases and there is a decrease in the filter pressure value. Your dispersion quality decreases, means the filter pressure value increases, so that dispersion quality is poorer. The last one, what we are talking about on the quality side, LLDP carbon black, it's a 50%. The without OD reduction, and the left hand side, the pellet, a good jetness, dispersion, good quality dispersion, and the smooth surface of the pellets. And the right hand side, it looks ugly and dispersion very poor. And because of the agglomerated, we see that lot of agglomerated particles because of the clearance. When the clearance increases between the barrel and the screw, the particle dispersion means, what is dispersion? Dispersion means the breaking the agglomerated particle into smaller and smaller. That is called dispersion. If the gap is increases, the dispersion quality drastically drops down. In the carbon black, we set as a benchmark ourselves up to 3.55. And if you say the first kneading section 1.5 millimeter per side is a 0.75, it is acceptable. After that, there is a sudden shoot up, sudden jump, because when you do the OD reduction of the first kneading 1.5, second and third kneading 1 millimeter, the dispersion quality reduces. It's almost double, 6.2 bar per gram. And after that, your filter pressure value started tripping. That shows the dispersion is very, very poor. That's an indication. And so that way, you need to change your elements. You need to work on the measurement. The another example I'm giving you on the calcium carbonate, polypropylene calcium carbonate, where you're talking 85% filler. This product looks very shiny and round shape, smoother. When you chew it, there's no powder formation, means there's no breakable. I mean, it gives some elongational effect. And then the right hand side, after the OD reduction, the poor pellets quality and dispersion is very poor. You see the still calcium carbonate you can see on the surface of the pellets. And the last case studies, we are going on the output enhancement. When you do the OD reduction, how the output drops down drastically. We have selected here similar polypropylene, TAL and 40%, and LLDP, additive blue, master batch, monopigments, LLDP, and 50% carbon black. And one is a split feed method on the polypropylene. Second application, we have selected 100% premix. Third is also 100%. We have selected a extruder model is a 40 millimeter omega H class. And here we have selected no OD reduction. Second one is 1.5 millimeter OD reduction from the intake to the end. Complete OD reduction. And also second, the last one, 3 millimeter from intake to the last. And during the split feed, because you're feeding talc from the side feeder, but first section will not affect much on the quality. When you start doing the OD reduction from the second section, then the quality drops down and the output drops drastically. If you see the no OD reduction, the throughput at 600, 200 kg per hour, and at 800, similarly, throughput increases to 300 kg per hour. If you do the first kneading section, means the from intake to the end, 1.5 millimeter OD reduction, we are getting 170 kg per hour. Means the drop of the output is 15%. And similarly, when it is come to 3 millimeter OD reduction, means 1.5 per side, we are getting 120 kg per hour. Means there is sudden drop in the throughput. And the drop of the output is 40%. When the output increases, okay, and slight increase in the throughput, 1.5 millimeter per side 0.75. If you see, the drop of the throughput is 16%. And similarly, in the 3 millimeter OD reduction, the drop of the output is 43% and 170 kg output. And similarly, SME, specific mechanical energy, the wear pattern means the reduction of OD reduces, wear increases, there is a SME increases, means power consumption increases. No OD reduction 0.17 specific mechanical energy. Similarly, at 800 RPM, 0.17. But when you do the OD reduction, 1.5 millimeter OD reduction, 0.1 made, there is an increase in the power consumption. And similarly, even at 800, slightly increased. In 3 millimeter OD reduction, 0.2 and 0.2, it is not acceptable because, and we are the extruder is consuming high SME, high power consuming, and slightly increasing. If you say 0.8% increase and 17% at the 3 millimeter OD reduction. Similarly, at 800 RPM, 17%. Second application, what we are talking about, the 100% premix LLDPE with a blue pigment. Similarly, here, no OD reduction, we are getting 85 kg per hour, and in 800 RPM, 105 kg per hour. The moment if you reduce the OD 1.5 millimeter, we are reduce the throughput 58, and similarly at 800, 71. If you see here, there is a drop of the output at 600 RPM, 1.5 means your throughput, the conveying efficiency drops down and dispersion quality drops down, almost 31% drop in the output. And in the case of 600 RPM, 76% drop. There is a drastic reduction on the throughput. In 3 millimeter OD reduction, 1.5 per side, 20 kilo. Then there is no point in running the extruder if you're running at 20 kilo and the 40 millimeter. And also in 27. Means this color master batch has to be taken care because the dispersion and the throughput both are important. We need to check your wear pattern. Similarly, in the SME, the power consumption as the wear pattern, wear increases, there is a SME slightly increase in both the sides. Even at 600 RPM, also even in 800. The last in the list, the final application was 100% premix, the combination of LLDP, carbon black, 50%. No OD reduction, we are getting 200 kg and 220. There is a slight increase in the throughput and the RPM increases. Similarly, in the 1.5 millimeter OD reduction, we are getting 120. There is sudden 80 kg drop, means there is a 40% drop in the throughput. Similarly, even in the 3 millimeter OD reduction, there is a 90% drop, means hardly 20 kg. And even in 800, similarly, it is going to happen. There is a drop and the throughput 54 at 800 means it's a 1.5 millimeter OD reduction, and 3 millimeter OD 100%, almost zero, means there is no movement, there is no forward conveying of the your final product. Means you have to replace when the moment if it is cross 3 millimeter means 1.5 millimeter per side. You are talking about the OD reduction because this is one phenomena so that we can understand which zone is a wear pattern. Even though if you increase the RPM, maybe after 1 month, again the wear pattern increases. So that again you need to replace. But you have to think how you can work out your wear pattern, and also you need to check check what you call it is a maintenance checklist, so that on the every 3 months, every 4 months. And similarly, SMA also, when the OD reduction of the happens 1.5 millimeter, there is a increase in the power consumption. And finally, the wear impact quality and the output. We carried out the study of the OD reduction, started from 0.6 millimeter to 3 millimeter using omega 40H class. What the final findings from us, the increase in the wear, okay, decreases the tensile strength. The wear increases, decrease in tensile, flexural modulus. The first kneading section, 2 millimeter means 1 millimeter per side, and in the second kneading section, 1.5 millimeter, and third kneading section is also 1.5 millimeter in the split feed method for the polypropylene tar acceptable. Behind that, you need to check the wear pattern. And increase in the wear, okay, impacted dispersion quality. And the first kneading section zone 2 millimeter, and second and third is 1.5 millimeter in the premix method is accepted. Behind that, again, we need to check the wear pattern. And this is the quality. Now we are going to the throughput. Our findings in the split feed method showed 1.5 milliliter OD reduction, like 15% output drop. And similarly, in the case of 3 millimeter OD reduction, 40% OD drop. That's a max we can do that. After that, then there is no conveying efficiency. And premix showed a 35.5 in the case of color master batch. The output drops in the 1.5 millimeter to the OD reduction 83%, and also 3 millimeter the reduces drastically. 35 points percent is output drop, and almost 83% means nothing. It is hardly 10 kg per hour.
Here is our second polling question. Please select your answers from the list of options displayed on your screen. You have 30 seconds to select. Are you facing any of the challenges as mentioned in our slides? Do you like Steve to contact you to offer best solution? Yes, no, or not sure? All right, 3, 2, and 1. Let's see the result. 33% says yes, 0% says no, and 67% says not sure. Also, if you have any questions on the ongoing webinar, please drop into the Q&A tab at the bottom of your screens and please ask your questions. Let's go back to Dr. Prakash to continue with the webinar.
The effect of wear ROE, I will hand it over to Raghavendra. Raghavendra, please continue.
Thanks, Dr. Prakash. That was a very good presentation. In fact, you have simulated the condition in your lab without waiting for the actual wear to take place, and made a report on what is the effect of wear, how is it going to affect on the quality and also the output. But there is something else that we need to see from these results are, it is not only the effect on output or the quality, there is also economical loss that we are going to see if it is not addressed properly. That's what is my observation from your experiment. The main thing what I observed from this experiment is there is going to be excess power utilization, extra manpowers or extra hours are required, and a loss of revenue and profitability, inability to meet customer commitments. These are some of the main reasons, the effects that what we can see. Let's take an example from the actual output, what we can see from a non-worn out elements and also already the worn out elements. If you consider 500 kg per hour as a output and conversion cost of about $1.5 per kg, and considering 80% as its operating cost, we'll see from the table that when you are getting an output of 500 kgs per hour and considering 6,000 hours in a year as your productive hours, from this you will see there is about 4.5 million USD of revenue that can be generated when the elements are in good condition and there is no much wear. That means your total profit is about 900,000 US dollars. Whereas if you assume a drop of say 10% of output, from the 500 kg output of a extruder. Say you are getting an output of 450 kgs per hour, and the same number of hours considered for the calculation, you will see here that there is only about $4 million as the total revenue, and your profit from that is just $486,000. There is almost 40% to 45% of reduction in your annual income just by ignoring the wear out. So from this, what we understand is by regularly monitoring the wear, by understanding the wear pattern, and by keeping stock of the elements what you require for your configuration and replacing it at a regular interval time, you are bringing back the original condition of the extruder. Thus, you are getting the maximum efficiency from your extruder. Thus, you are getting your regular income. So the effect of quality is mainly it is increase in rework to get the benchmark quality. More number of passes may have to be taken to meet the benchmark quality. There is a lower dispersion and mechanical properties. Extra use of additives or process stabilizers. Aesthetics of end product, that is white patches or dull color. Rework on end products and dimensional variation of mold parts, etc. We have so many features in a extruder that sometimes we ignore the downtrend of output or quality, and we try to use the features of the machine to match to that. So in fact, not replacing the elements and just using the features to get back your output or quality is not a good idea. So there is also an effect on end use customer, that is the loss of customer confidence. Say, for example, you have a very huge batch of some 100 tons and the quality is not met. There are all possibilities that entire batch is rejected and it's a total loss. So the effect of wear is not only on the quality, it's also from confidence, customer confidence level, it's a big loss. Chances of other competitors capturing the market, low employee morale within the organization, and issues in consistency and performance of compounds supplied to customers. So from this experiment, we learned that it is because of the wear, it has so much impact on quality, output, economic losses, from powers to manpower and all other losses. So steer can provide most suitable solution to overcome these problems. We have wide range of MOC applications in wear resistant series, in corrosion resistant series, with powder metallurgy, soft core, pressed welded and surface coated. We have different options to provide to our customers so that the life or the wear can be postponed and you can get a maximum benefit out of your investment. We have our own proprietary MOCs in acrylic grades like WR5, WR6, WR7, WR10, CR5, CR6, and CR15. As the number increases along with WR grades, so the wear resistance also increases, and in the corrosive grades, the corrosion resistance also increases. The range or size of parts that we supply are from diameter 10 mm to 300 millimeter diameter of extruders. A database of computer machine parts, that means we have about more than 6,000 plus database readily available with us to supply spares for our customers, and we manufacture with the best lead time, that is the reduced lead time due to in-house design and manufacturing facility. Our quality of product are 100% inspected and we ship only if it is 100% okay and there is no compromise on the quality. And we have all OEM grade products. Parts quality will be at par with the OEM supply. And there is also a competitive advantage, value for money. The highest quality parts at reasonable prices. We also compete not only with the quality, but for also prices. So thank you, Dr. Prakash, for the wonderful session. Now we have another poll question. I request Shraddha to.
Thank you, Raghavendra. Yeah. Let's see what we have on the third poll question. Please select your answers from the list of options displayed on your screen. You have 30 seconds to select. Considering the impact of wear on output and quality, as well as cost of elements, will you like to discuss with us and identify best time for element replacement? yes or not sure. All right, 3, 2, and 1. The poll stops. Let's see the results. 71% says yes and 29% says not sure. Also, if you have any questions on the ongoing webinar, please drop into the Q&A tab at the bottom of your screens and kindly ask your questions. Let's now go back to Dr. Prakash for the final sessions of the webinar. Let's move now on the Q&A sessions, and over the next few minutes, Dr. Prakash will answer your questions. So let's see what the first question is. So please drop your questions, if there are any, to Dr. Prakash in the Q&A tab. And thank you for all for joining this webinar. We now conclude today's webinar once again, and we thank Dr. Prakash Hadimani and Raghavendra Jayaram for their kind attention and answering the questions. Once again, we thank all of you for taking your time to attend today's session. We also request you to provide your feedback on today's webinar by email. The email ID is provided on the link shared at the time of registration. Thank you and have a great day.
Thank you.
Thank you everyone for participation and thank you.